Hi, my name is Wanhua Li. I am a PhD student at Tsinghua University and now present our paper learning probabilistic ordinal embeddings for uncertainty-aware regression. According to recent research from MIT and Amazon, labels are not perfect. We show some examples from their website. We observe that some labels are simple mistakes, while others are hard to judge. In fact, there are some uncertainties in label assignment. Modeling uncertainty has an important practical impact. For a deep neural network, it's important to know what it does not know. A natural question is whether the neural network itself has modeled the uncertainty. Unfortunately, recent researches show that DNNs tend to give overconfident predictions. Therefore, it is crucial to equip existing deep models with uncertainty. There are two main types of uncertainty: model uncertainty and data uncertainty. In this paper, we focus on data uncertainty. More specifically, we focus on modeling data uncertainty for regression problems. We first present the formulations of three popular regression methods. The direct regression method employs learnable parameters to project the point embedding into a scalar value. The model is trained with L1 or L2 loss. Classification-based regression methods discretize the target space into C-classes and treat regression as a classification problem. Cross-entropy loss is utilized to optimize the networks. Ranking-based regression methods construct C1 binary classifiers for C-classes, where KTH1 predicts whether the rank of sample X is larger than K. Meanwhile, the existing uncertainty method replaces the point estimation with a probabilistic distribution in the output space. Although this strategy can be applied for the direct regression method, it cannot be applied for classification-based regression and ranking-based approaches. Both classification-based regression and ranking-based approaches have multiple neurons in the output layer. These neurons are highly correlated, so it is difficult to choose a suitable distribution to replace them. In this paper, we propose to learn probabilistic ordinal embeddings which represent each data as a multivariate Gaussian distribution rather than a deterministic point in the latent space. Deterministic unordered embeddings represent each image as a point in the latent space without considering the data uncertainty and the ordinal property. By contrast, probabilistic ordinal embeddings learn a distribution following the ordinal constraint in the embedding space. Given an input image X, we first obtain the mean and diagonal covariance of a multivariate Gaussian distribution respectively. Then we sample embeddings from this distribution with the reparameterization trick. Lastly, the sampled embeddings are sent to a popular regressor for prediction. Under the above framework, we can have different formulations for different regression methods. The uncertainty mainly spreads probability mass across the locations that correspond to the neighbors of ground truth value. For example, if we estimate the age of a person as 30, then his uncertainty in the embedding space depicts that he is around 30. Therefore, we expect that the ordinal relation in the target space can be preserved in the embedding space. Therefore, we propose the ordinal distribution constraint to enforce the ordinal relations in the embedding space with the symmetrized KL divergence or 2 Wasserstein distance. We conducted extensive experiments to validate the effectiveness of the proposed approach. Experimental results on the age estimation task and historical image dating task demonstrate that our method improves performance and achieves very competitive results. We also conducted experiments on the image aesthetics benchmark. Our method achieves similar results. Knowing what a model does not know is critical for many real-world applications. We aim to estimate when an input image can be reliably predicted or not. Since the data uncertainty is modeled in the diagonal covariance, we give a per-exemplar uncertainty score using the harmonic mean of the predicted variance. We show the correlations between the uncertainty score and different performance metrics on 2 corrupted test sets. To quantitate the correlation, we adopt Kendall's tau correlations. For the curves of 3 subfigures, the results are 0.956, -0.733, and 0.778, respectively. We see that the proposed uncertainty score correlates well with the performance of our method, which demonstrates that our uncertainty score can be regarded as an indicator of the reliability of model predictions. Thank you for listening.